Hi guys, so now let's work out the solution here, right? So this is just to recap, this was a uniformly charged shell, right? The charges are distributed uniformly, and if you care about, you have the value of sigma, which is the charge per unit area. You don't need that here, right? And so now we need to know what is the variation of the electric field and the electric potential. Now let me just mark the distance capital R, right, and I'll do the same thing here. So these 2 points, these are at capital R distance, right. Now let's look at the electric field behavior. So now we bring a charge from here, and what is the field? So we'll experience some force, and the field is going to be exactly the same as if the outside the shell, right. The field will be exactly the same as if all the charge was concentrated here. So for distances greater than R, this curve and this curve, they would be exactly the same, right. So for distances greater than R, this curve and this curve, they would behave, the shape would be exactly the same. So let us say it reaches some value here, and then it'll have a decline from here, right? It'll go to 0 quite fast, right? Now the question is, when you cross this point inside, what happens? Now again, we'll not do it here, but we have seen in previous videos that we can do a quick application of Gauss's law, and we can see that the field inside is going to be 0, right? If you take a Gaussian surface, right, it's symmetrical, so E is constant if there's some electric field, and then we know that charge inside is 0, so electric field inside is going to be 0. So which means at this point the field will dramatically, so field goes up, and suddenly from here the field falls to 0. So after this point the field is going to be 0. This is going to be my electric field, right? So it goes up, and then from here, and there is a discontinuity here, right? There's a discontinuity into the graph here. So here it is 0, and here it is some value, and then it goes down. Now in case you're wondering what is this value, we can very easily find out what is the value. Value is going to be this value, right? This value is going to be Q upon R square, right? And what is Q? Q is going to be nothing but sigma into 4 pi R square. So this would be K into sigma into 4 pi R square upon R square, right? Cancel this, but I'm not worried about the exact value, but if you want to find this, we can find out this point as well. Okay, now let's come to the electric potential. This is a little more interesting, right? So now let's first look at the value. So now when it's outside, right, again, when you're outside the sphere, it behaves exactly like this behaves, right? So there V and E is going to be exactly the same. So now we'll find the value of, and what is the relationship outside this? It's going to be V is equal to, again, KQ upon R. I'm not going to write sigma and all that, and you understand that, right? So there's a value, and let's say there's some, so here this would be KQ upon capital R. That would be the value at this point, right? So here this is going to be that value, and then after that it will decline, and it will decline as 1 by R, right? Okay, now next question, which is more interesting. Once you're inside this, then what happens, right? Now very often when I ask this question to students, the answer I get is electric field is 0, so potential is 0. That's not correct. Why is that? Think about, again, whenever you get these questions, try to bring in mathematics and your intuition. So what does the intuition tell us? Intuitively you know that the definition is electric potential is the work done by an external force to bring a unit charge from infinity to that point. Now when I'm bringing it from infinity, there's a push, right? There's a push, so I have to work harder, so more work is done, more work. So when I bring it down, when I bring it close, more and more work is done. So the total work done keeps going up until this point. When I enter this, what happens? There's no more force. So once you enter this, there is no more force here, which means, is there any extra work done? No. Right? So the work will go up, and after this point there is no extra work done. So here the total work done remains constant. Right? So this is going to be the graph, and one way to verify this, we said that E equals minus dV by dr. Here what is my E? Electric field is 0, which means my V has to be constant, because derivative of a constant is 0, right? So it stacks up, it matches our mathematical requirement. Right? So this is how we'll plot the E and V for a spherical shell. And the last question I'll give you, which is plot the same thing, exact same thing, but now this time for a solid sphere, okay, not for a shell. So I'll draw this for you. So So this is a solid sphere, right? There's a center, radius is capital R, and there is charge throughout, right? It's charge throughout, uniformly distributed, right? Here it was only at surface, here it's all inside, right? It's totally filled up. And if in case you care about the density, charge per unit volume is given to you as rho. And now exact same thing, kindly help me understand. Number one is the variation of electric field, right, with distance, and second, the variation of potential with distance, right? So work this out, and in the next video we'll discuss the solution. Thank you.